In this video, I will be showing you how to find the equation of a polynomial function with given characteristics. To do this, we will be relying on the linear factorization theorem, which states that we can write any polynomial in terms of a leading coefficient and linear factors. So let's start with an example. I want to find the equation of a degree 3 polynomial. So that's telling us how many zeros it will have. And I'm going to start by saying it has zeros of -2, 1, and 4. And we have to be given one last piece of information, which in this problem is going to be f of 2 is equal to -16. So remember, linear factorization theorem says I can take any polynomial function f of x, write it in terms of leading coefficient and its linear factors, where each of these c's is one of our zeros. So we have our 3 factors to go with our 3 zeros. Let me fix that. Leading coefficient I'm calling the an. So let me start by plugging in all of my factors. Our function we know is going to look like our leading coefficient, x plus 2, because we are plugging in a -2, and so we have x minus a -2, which gives us x plus 2. And we have an x minus 1, and we have an x minus 4. We always want to subtract off the 0, so that means on the first one we switch the sign of the negative to a positive, and positive 1 and positive 4 become negatives. Now what we really need to figure out here is what is that leading coefficient, this piece right here. And this is where that last piece of information, f of 2 is equal to -16, comes into play. I plug -16 in for the y position, which is what this is telling me to do, then 2 must be the x. So I'll have 2 plus 2, I'll have 2 minus 1, I'll have 2 minus the 4. And from here I'm just going to simplify everything that I have to solve for that an. So -16 is equal to an times 2 plus 2 is 4, 2 minus 1 is 1, and then 2 minus 4 is -2. When I multiply all those together, I get a -8. To get that an by itself, I must divide by that -8. When I divide -16 by -8, I get a 2. So now I know what that last piece of my puzzle is. I know what that leading coefficient is. So I can come back here and I can write the equation f of x is equal to 2 times x minus, or x plus 2 rather, x plus 2, x minus 1, and x minus 4. Now, some instructors or some textbooks might request that you multiply this out. This should be a pretty standard exercise, so at this point we would have to fully distribute each of these linear factors and we would get our degree 3 polynomial. I want to do another example. We're going to once again take a degree 3 polynomial. This time, I'm going to have zeros, given zeros of 3 and -2i. And we're also going to be told the y-intercept is equal to 36. Y-intercept 36. A little different than the last case, because if we look here, it looks like we only have 2 zeros. When we're told it's a degree 3, that should be telling us there should be 3 zeros. So we have to figure out what that third one's going to be. And remember, imaginary numbers always come in pairs when we're looking at the zeros. We will always have complex roots that come in pairs, and they will always come with their conjugates. So if we have the imaginary number -2i, well, that tells us we also have a root of positive 2i, and that would give us our 3 zeros to go along with that degree 3 polynomial. We knew there should have been 3 zeros. The other thing that's a little different is we're given a y-intercept. Last time we were given the f of 2 is equal to -16. It doesn't seem like this time we're given a point, but we really are, because the y-intercept is really a point. So once again, we're starting with this idea that any polynomial can be expressed as leading coefficient times its linear factors. And because this was a degree 3 polynomial, there should be 3 of those factors. So we'll plug them in. Our leading coefficient times x minus 3 because we have to switch its sign. Then we'll have x plus 2i, again switching its sign, and x minus 2i will give us all of our linear factors. So now we're going to plug in that extra bit of information, the y-intercept, the 36. And to do this, we do need to think of it as a point, which said we can do. The y-intercept is just a point. You need to remember it is really just the point 0, 36. Y-intercept, the x value is always 0. So I'm going to plug in my 36 for my y, looking for that leading coefficient, plugging in zeros for my x's. Now we're going to do the same thing we did in the last case, which is just to simplify. Have a 0 minus 2i there at the back end. I went ahead and simplified that. I know it's just going to give me the negative 2i, but let me write that out. So we'll have our 0 minus 2i. So now we're going to simplify, which I know that 0 minus anything is just itself. So we have the negative 3 times the 2i times the negative 2i. And we want to multiply these together. It is always easiest if you multiply your complex conjugates first, in this case just the two imaginary numbers. 2i times a negative 2i is a negative 4i squared. And then remember, I squared is just a negative 1. So if we have a negative 4 times that negative 1 here, that's just going to turn that into a positive 4. And so we will have negative 3 times positive 4, which of course is a negative 12. And if I drag that down, then our an will just be equal to negative 3 in this case. So now I know that my leading coefficient, the an, is negative 3. I'm going to rewrite the equation. F of x is equal to our leading coefficient, the negative 3, x minus 3, x plus 2i, clean that up, x plus 2i, x minus 2i. And that would be our final equation. Right, I want to look at a third and final problem. This time we're going to take a degree 4 polynomial. It's going to have an extra 0. Degree 4 polynomial. We are told 3 of the zeros of 3, negative 1 rather, negative 1, 2, and 2 minus 3i. And we are also told that f of 3 is equal to a negative 40. All right, so we have the same problem as we did on the last one, that we're only told 3 of the 4 zeros, or we're told 1 fewer 0 than what we really need to have. So we need to start there. We need to figure out what that 4th 0 is supposed to be. And we know if we have these complex zeros, we always have to have their conjugates. So that means the other one has to be 2 plus the 3i, not just the minus, but also the 2 plus 3i. And that gives us our 4 zeros. So now that we have all 4 of our zeros, let's write out what this function will look like without any numbers plugged in. So our f of x is equal to leading coefficient an. And we'll have our x minus the first 0, c1, x minus the c2, x minus c3, and then finally we'll have the 4th factor, and we will have 4 this time because we have a degree 4 polynomial. So 4 factors to go with our 4 zeros. Now if I plug in my numbers, f of x equals, well, we don't know what the leading coefficient is yet. That's what we still need to find. But we do know that our first factor will be x plus 1 because we switched the sign of that negative 1. Then we have x minus the 2, again switching the sign of our 0. Let me shift this over just a little bit. And then next we'll have our x minus 2 plus 3i, because we do have to remember to distribute that negative, the negative from the c right here. We have to remember to distribute that really, to both of our two factors. So we have x minus 2 plus 3i, and then we have x minus 2 minus 3i. That is the 0 in red, again distributing that negative to both the 2 and the 3i. And now is where we're going to use that last bit of information. Right here, the f of 3 is equal to negative 40. What I want to do is I want to plug in that negative 40 for my f of x, while at the same time plugging in the 3 for my x. So I'll have 3 plus 1, 3 minus 2, 3 minus 3 minus 2 rather, plus 3i, and then 3 minus 2 minus 3i. And now if we start cleaning that up, if we start combining our like terms, we have our leading coefficient, and we're going to have a 4 in the first parenthesis. 3 minus 2 is 1. 3 minus 2, we get a 1 again, 1 plus 3i. And then we have the 1 minus 3i. We can still see that those complex roots look very much like conjugates. We have just the sign in between the real component and the imaginary component switched. Continuing to multiply, simplify this, we have our 4 times 1, which is 4. And just like we said in the last example, easiest to work with those complex numbers before we try to distribute the 4 across. So I have my 1 times my 1, which is 1. The imaginary I component has to cancel, negative 3i plus 3i cancels. And then we have a minus 9i squared. And just like we said in the last case, that I squared is really going to become a negative 1, which changes that 9 to a plus 9. So we'll have negative 40 equals an times 4 times 1 plus 9 is 10. So negative 40 equals our leading coefficient an times 40, which means that our leading coefficient an is simply equal to negative 1. So now we're finally to a point that we can write out our polynomial function. Our function f of x must be equal to the negative 1, or I can just put that negative in front. Then our first factor x plus 1, x minus 2, x minus 2 plus 3i, and the x minus 2 minus the 3i. Clear this. Minus 3i. And now that we have our leading coefficient along with our zeros, we know exactly what the polynomial is supposed to look like. Hopefully this has been informative.